Now, it kind of turns out that the first law of thermodynamics is really important to meteorology, and that's kind of how meteorologists, predict the weather. How hot is it going to be tomorrow? Kind of what they do is they say, okay, well, I have a system right over there, and if the temperature is going to go up, internal energy goes up, then that can happen either if I add some heat into the system, so we can increase our air temperature by adding heat into the system, or as we do work into the system. And how we do work into the system is we can increase the pressure, and that's kind of one of those things that you see is what's the pressure? Is it a high pressure system or a low pressure system? So we can increase the pressure. We can add heat coming in several different ways. We have the sun shining in on us, so that's going to be heat into the system. Earth is emitting some radiation, and that's also going to be heat. When there's condensation, that also adds heat into the system. And last but not least, when air makes contact with the ground, that's another form of heat that can increase the air temperature. If we consider the process to be adiabatic, which was actually a pretty good approximation for what's going on in the atmosphere. Remember, adiabatic means no heat into or out of the system, so kind of got my proverbial system. All we have is going to be work that is done to the system. Then essentially, then air temperature is going to rise as the pressure increases, or if the pressure decreases, then air temperature is going to fall. Now, how do we kind of do that? Well, if we had a blob of air just like this, we can kind of call a blob of air a parcel, and as the air parcel maybe moves up in the atmosphere, well, the pressure is going to decrease. So we would expect the temperature to go down, right? There's less pressure as we go higher up into the atmosphere. And that's actually also a pretty good approximation where we kind of treat these air parcels as being these like giant big bags of air, and these air parcels kind of move up and down and don't really mix around too much with the air that's around them. So air goes up, it cools off, air comes down, it warms up. You can kind of think of this almost like a piston, where here we have a big chunk of air, a parcel if you will, and here we have a piston. As this piston expands, so it gets larger and larger and larger and larger, well, it's actually doing the work, and so we would expect it to be cooling off as we work our way up in this direction. If we were compressing a piston, kind of like I compressed that fire piston, kind of working away in this direction right there, we would expect it to be warming up. So as air moves up in the atmosphere, it tends to cool off. As air moves down in the atmosphere, it tends to warm up. So really, this is kind of how meteorologists predict, where the cloud deck is going to be. They say, okay, we got these chunks of air, and they're going to tend to rise up, and they're going to expand and expand and expand. And as it expands, it's going to cool down. And it turns out we know how much that's going to be for typical air. Turns out that the magic number is about 10 degrees Celsius for every kilometer. So as air rises up, every kilometer it rises, it's going to cool down by 10 degrees. Now just kind of keep in mind that this works out to be about 5.5 degrees Fahrenheit for every 1,000 feet. And maybe you know exactly what I'm talking about, where it's wintertime and you're driving up the side of the mountain and you're looking at the thermometer gauge on your car and it's at 35 and then 34 and 33 and then 32, and you're like, okay, there could be ice on the road. Kind of what's going on is you're going up in the atmosphere. It tends to be cooler. So suppose we had just a chunk of air that was at 25 degrees Celsius. At 1 kilometer, it's going to drop by 10 degrees, it's going to be 15. Goes up another kilometer, drops by another 10 degrees, it's going to be 5 degrees. 3 kilometers, -5, 4 kilometers, -15, and so on and so forth. Now, it turns out that air is just going to naturally tends to rise and expand as long as it has a higher temperature than its surroundings, and once it gets cooler than the surroundings, it tends to sink, right? Hot air rises, cold air tends to sink. So take a second and see what you think would happen if you had a air parcel with a 10 degrees Celsius temperature at the ground, and then what's it going to be at 5 kilometers up? So 0, 1, 2, 3, 4, and 5. Well, you would expect that it's going to drop 10 degrees for every 1,000 feet, so 0, -10, -20, -30, and -40, and that's going to be in kilometers. So you'd expect it to be -40 degrees Celsius at a height of 5 kilometers. Now I do just want to take this a little bit further than what the book does. If we have a chunk of air right down here, and we say, well, what's going to happen? How are we going to get a cloud to form? Well, we got this chunk of air, and the parcel is going to rise up, and it's going to expand, it's going to cool, and at some point it's going to condense. So what do we need for a cloud? It turns out we need three things. First of all, we need water vapor. We can't have a cloud is essentially mostly water, so we definitely need water vapor. It also helps to have a condensation nuclei, something for that water vapor to stick to. Turns out that water doesn't stick to itself as easy as maybe I've led you to believe up until this point. And we also need a power source, something to kind of get this guy going up in the atmosphere. Now that power source could be the sun, it could be a mountain, or could be any number of things. Now, an example that I do in class is I usually take a bottle and I squeeze it and say that I'm doing work to it, and it warms up, and then I release it, and if there's some smoke and some water vapor in there, you can actually form a cloud, but it's actually so weak I couldn't get a video of it. However, here we have the same thing, only actually I want to build one of these things where we have this guy and he hooked his bike pump up to this bottle, and he's doing work, so it's quite warm, and then he goes ahead and he takes this thing off, and the rapid expansion of the gas allows a cloud to form inside of this bottle. So it's cooling off, and it causes the water to coalesce. The reverse is true. Now he's doing work to the gas, and it tends to evaporate. Again, you pop the lid off, and a nice little pretty cloud. Kind of an interesting application of this is going to be something called a Chinook wind, and also it kind of explains why the Pacific Northwest is kind of rainy all the time. So if you think about how we have the Pacific over here, and we know that that's going to be some warm, moist air, and then we have these things called the Rockies. And what's going to happen is this warm, moist air gets blown upwards, and as the air rises, it expands and cools and cools and cools. And if there's enough water content, then actually it's going to start to rain, and all that water is going to leave. And then we're going to have some cold, slightly less moist air on the other side of the mountain, and then it's going to go down. And what we're kind of left with at the end of the day is as it goes down, it's going to warm up, and right over here we're left with this warm, dry wind. And what the Indians called this warm, dry wind was a Chinook, which means snow eater, and really it all boils down to the first law of thermodynamics. Now, occasionally we get this funky little thing called a temperature inversion. So if I had a chunk of air and I let it go up in the atmosphere, it's going to get bigger and bigger and bigger, and as it does so, it's going to get cooler and cooler and cooler. So this might be cool and this might be warm, and essentially it's going to keep on rising until it's at a larger temperature than its surroundings. But what would happen if for some reason we had some warm air that was sitting on top of some cold air? Well, what that is that's actually called a temperature inversion, and what that actually does is it kind of acts like a blanket, and it says, maybe this air can't go below this warm patch right here. Now, what a temperature inversion kind of does is, like I said, it just acts like a blanket, where here we have some warm air, and it just says to this air right here, nope, I'm sorry, I'm warmer than you, you need to stay below me. And you may see this like from a campfire sometimes, where here you have a nice little campfire going on, smoke's rolling everywhere, and then it kind of gets trapped up at this layer right over here. Another example is going to be LA. The smog in LA is absolutely horrible. I'll show you on the next two slides. We did a field mission there. But what we have is we have LA, and LA sits on the Pacific, and the Pacific is very cold, trust you me. So here we have some relatively cool air, but LA sits a bit up against some mountains, and we have some hot air blowing from the desert just right over there. So hot air over cold air, we call that a temperature inversion. And what that does is you get the cold air blowing off the ocean, and it's trapping all of this stuff right over here, all this pollution. And all that pollution is essentially called smog, and it's pretty nasty to be breathing in LA nowadays. Now, we did a field mission with NASA in LA, and this was actually a P-3B Orion aircraft, and we were just flying through the smog, measuring all that stuff. You can kind of see, I'll kind of sketch in some of these layers right here. All of these guys are temperature inversions where all of the pollution was trapped below it, and I don't know about you all, but I'd be relatively unhappy to be down here. One day I left LA and I drove up to Big Bear Lake, and you can kind of see I've just outlined right over here. So LA is under there, and pretty much there's a temperature inversion right there, and all of this pollution is just kind of trapped into the valley. You can see the mountains. So right over here we got the warm air blowing off the desert, cold air blowing off the Pacific, and again, not a good day to be a person in LA.